Hello, everyone. My name is Olivia Curtis. I'm a postdoc at the Penn State Extraterrestrial Intelligence Center. My background is actually in galaxy evolution and large-scale structure, so this is really the first study project that I have been a part of. But nevertheless, I'd really like to thank the conference organizers for allowing me to give this talk today. So I will be talking about a relatively untapped subfield of what I feel is a relatively untapped subfield of SETI, which is going to be the investigation for technosignatures from entities trying to tap energy from black holes, ranging from solar mass black holes to the main focus of this workshop, the supermassive black holes at the center of every galaxy. So most of this talk is actually going to be a summary about the Dyson Minds 2025 workshop, which was held in June 2025 at the MIT Center for Brains, Minds, and Machines, in collaboration with Penn State, MIT, and the Harvard Center for Astrophysics. And it was truly an extremely fun, super interdisciplinary workshop where we talked about what the the observability of what an entity around a black hole would leave, what technosignatures would we actually be able to observe, as well as as well as looking at some of the more post-biological aspects of what would an entity taking the form of a large computational swarm around a supermassive black hole look like? What would their behavior be? How would you design such a large distributed computing cluster, and how some of the behavioral aspects of why they would be going after the energy around a supermassive black hole in the first place. So just to define what we mean when we talk about Dyson minds and their motivations. So the premise of this workshop is going under the assumption that these are hypothetical entities based on the foundational work of Freeman Dyson and Irving J. Good, which represent advanced post-biological artificial intelligences operating at galactic or intergalactic scales. So previously, many authors have imagined Dyson spheres as tools for computation, as we've talked about in our previous talks, that can extract low energy entropy from starlight to perform some computation. Well, a logical consequence of this, when tying this in with Irving J's good idea on superintelligences and singularities, is that once you have sufficiently complex computational um, power, eventually that can learn to self-replicate other computers or other algorithms. You eventually reach a singularity where you derive some form of a superintelligence. So in the context of Dyson minds composed of individual, so in this case where our superintelligence is going to be this Dyson mind surrounding some black hole that is composed of individual swarm elements, and the nature of these entities fundamentally become intertwined with their observability. So to tie this all together, this really was a super interdisciplinary field of attack. So we're tying in themes from SETI and types of technosignatures that we can imagine, the astrophysics surrounding black holes, AGN, and their surrounding environments, the engineering constraints behind constructing such a swarm in the first place, the computer science that goes into building these complex algorithms and distributed computing with up to light years of latency, um, or light travel times of latency, the fields of artificial intelligence and ecology to describe what the behavior and different types of behaviors and what different types of observability families might those behaviors produce. So some of the questions of what might be observable about such minds, well, unfortunately, that depends on exactly what they do. We can't know too much like a virus trying to predict human behavior, but there are some principles from ecology that might be able to guide us towards understanding what type of data we need to be, or what type of signals in our data do we need to be looking for. Brains fundamentally need power, so minds might seek the most extreme energy gradients in the universe. For example, the supermassive black holes that exist at the center of every galaxy. Evolution might apply to these minds. They might change over time, and their goals and ambitions might change over time, which is of course going to change what observability signature they leave. So what exists, so what we see are those that prioritize survival and longevity, those that leave the longest window that we might actually be able to observe an actual technosignature. So our main strategy from the first day of this workshop was just to divide space of minds and behaviors into regions of similarity to help constrain what type of concrete SETI searches need to be done going forward. Just an example of some of these different consequences, physics from those computational Dyson swarm papers that I talked about previously might say that the optimal Dyson mind might prioritize computing, in which case you want super low temperatures, as low as you can get to maximize energy usage across the entire swarm, which might lead to larger swarms as you move farther and farther away from your energy source with super high latencies. Where one focused on engineering might say to reduce latency to speed up compute power, e.g., or for example, you might want to beam energy down to your compact object to help offset some of the waste heat that you're giving out, allow you to exist closer to the emission source. Whereas AI, one focused on artificial intelligence, might suggest odds of one versus many minds around a supermassive black hole. For example, if this mind wanted to try to remain coherent across all of its different swarm elements, they might require extremely low latency. So they're small, but may have maybe beaming more information to allow for faster communication between node to node. And so like just an example of imagine you're one of these minds trying to exist around a black hole, and your main focus is trying to hide. You don't want anyone to be able to see that you're there. So what are you going to do? You're going to want to try to reduce the amount of waste heat that you're giving off. So you might try to beam some of your waste heat towards the compact object, and you might bury yourself within the dust obscured region of these black holes, which I'll touch on in a second. So we can see how there's going to be a bunch of different interplay between how, or families of solutions of what types of things we might want to look for when digging through black hole data for signs of technosignatures. And because I want to take a moment to focus on why are we talking about black holes? Well, they're just the black hole in general is the largest energy gradients in the universe. And as I'll talk about in the next slide, if they're quasars, so super luminous in the optical and ultraviolet, these can be some of the most continuously luminous objects in the universe. And this idea of extracting energy from black holes isn't new. So this is actually from Penrose's first paper where he brings about his idea of what would become the Penrose process of extracting the spin energy of black holes, where he actually includes this one little figure which he uses as a thought experiment, but maybe thought of as a type of a form of SETI, where he imagines what a society might actually be able to extract energy using the Penrose process on a macroscopic scale. So here he lays out this kind of cartoonish figure of these beings that put some spherical shells around the black hole, and then they physically winch down macroscopic weights into the ergosphere of the black hole, where frame dragging begins to accelerate them, and they end up extracting some of the mechanical energy off of the winch as the weight starts to get frame dragged by the rotation of the black hole. So this idea has been out there, but it's really a lot of thoughts on extraction of energy from black holes have kind of stopped here up until like a few papers in the recent years. And I just want to highlight that this spin energy extraction is an extremely efficient process. 20% of spin energy from the Penrose process, whereas for like radiative efficiencies from accretion disks, you can get anywhere from 1 to 10%, depending on who you ask. And compared to the amount you get from nuclear fusion of with a 0.7% efficiency, black holes seem like a much more lucrative project if you're truly seeking to do the largest computations that you physically can. And supermassive black holes exist in every host galaxy. So they motivate these are excellent Schelling points, motivates behaviors, providing excellent places to either like try to hide in plain sight or to project power if you're the type of entity, if it's the type of entity that wishes to try to dissuade other people from taking the watering hole that it's already established itself at. So quasars, as I mentioned, are the most continuously luminous objects in the universe. And to tie into this theme of this workshop of all the different instruments that we could use to try to do technosignature searches. And I really think there's no better target to look for anomalies than around the active galactic nuclei, because they truly emit at every band in the electromagnetic spectrum, as well as neutrinos and gravitational waves. So we have like these hot accretion disks that can emit in the UV optical, these broad emission line regions with very signature emission lines, the dust obscuring torus at around 1 parsec away from the black hole, very bright in the infrared. And then you have jets that I'll talk about in a second that can produce energy up to very bright in the radio, but also gamma waves and also neutrinos and spherical shocks and shock waves. So what Martin Elvis has laid out here is just going off of sort of like a habitable zone for a star. What would the habitable zone of a quasar be with luminosity between 10 to the 10 to the 10 to the 12 solar luminosities? And when you're about 4 gravitational radii or about 1 parsec away, you actually reach temperatures around 15 to like 200 Kelvin. So like actual regions where you can put solid material or even biologic material around such a supermassive black hole. Now, I worked for a bit at the Blazar group and at BU with Alan Marsher, so I'm obligated to talk about jets for a second. These are like shoot out of around 5% of AGN and can extend for kiloparsecs. They can accelerate plasmas to relativistic speeds. Although extremely bright in the radio, you can have strong shock set form that can produce gamma rays and neutrinos. And so there's been quite a few study papers trying to investigate ways on how you can extract energy from jets like this. So the most fun one that I've heard is this idea of like almost like a watermill, where very far down the jet you put a large solar sail-like material that then gets ram pressured pushed downstream by the jet, and then you can extract some mechanical or orbital energy from that watermill as it falls back down to its original orbit. So all of this is just to say that there are a lot of places that we can look for anomalies or weird signatures from all of the data that's been collected over the past 40 years from AGN, ranging from the entire electromagnetic spectrum, neutrinos and gravitational waves. So I truly encourage people to start thinking about different ways that they might be able to look for some anomalies in these data. So I now want to briefly just go over some of the findings from the workshop on the nature of Dyson Minds, with the behavior of such minds, including cooperation, computation, and competition for a low energy fuel, may shape not only their architecture, but also their observabilities. Do black hole adjacent civilizations, some motivated questions. Do black hole adjacent civilizations even produce detectable waste heat? Is it possible to mask it? If we go back to this picture here, might an entity try to just bury itself in the dust obscured torus with as much dust around it as possible to try to completely hide its IR signature? Is that possible, or would the swarm elements just get completely destroyed and ablated by the amount of dust within their orbit? What are the limits of parallel computing when individual nodes are not fixed in space? And do modular high latency minds resemble naturally occurring noise, or do they exhibit detectable structure? Meaning, are there communications or the types of signals that they're emitting? Can we actually detect those as discernible technosignatures, or is it just going to look like noise or outliers in our outlier detection algorithms. So just briefly, we talked a lot about the taxonomy of Dyson Minds, so their hierarchies. So two key branches being whether or not they're engineered versus emergent, and if they're coherent versus incoherent, neither of which need to be mutually exclusive, but nevertheless is a fundamental taxonomy for how these things might come about through either natural or engineered processes. So engineered mind is what it sounds like, a mind that results from deliberate large-scale construction projects initiated by an advanced civilization, probably highly targeted towards efficiency, maintainability, upgrades. So we might be able to find like highly structured and patterned technosignatures, such as regular power modulations or transit light curves in the optical UV or even X-ray transits of some of these black holes and quasars. Whereas an emergent Dyson mind is one that can form from more natural evolutionary processes, may not be a single coherent entity and instead take the shape of fragmented entities. So these where each individual swarm element is effectively its own artificial intelligence that are all working together in this sort of ecosystem around this environment of the supermassive black hole. So perhaps leading to competition and potentially architectures that may be less efficient, redundant, or more heterogeneous. And then lastly, in our taxonomy, we discussed incoherent versus coherent minds are ones in which the computational and structural components remain bound together as a singular entity versus one that, due to the having latencies with travel times on orders of years, might put to the be a more incoherent mind of again a sort of ecosystem of minds all competing or working together for a singular goal. For time, I'm gonna skip that slide, but yeah, I just wanted to say that this so this was a lot. So we highlighted everything from behavior of minds to discussion on supermassive black holes, and I don't expect you all to have become experts in all of those fields. But what we've done is we've written a manuscript here that's one part a summary of this workshop and one part a literature review on what work has been done regarding SETI and black holes. So we hope that this is going to be an excellent resource for anyone looking to build on these ideas going forward, or to just help start building the case of knowledge surrounding what these types of entities, how their computational behavior might look like, and what type of observability signatures might we actually be able to draw from them. So my last couple of minutes, I just want to talk about next steps towards observability of these objects. So in 2014 started the GHAT project, whose goal was to place constraints on the IR impact caused by galaxy spanning civilizations. So those Dyson spheres that we've talked about in the previous talks in this session, how might that look like if instead of just one star having a Dyson sphere, how would the actual spectra of a galaxy change if we have thousands or millions or all of the stars within the galaxy covered within a Dyson sphere? One issue with modeling this in terms of galaxies is that the starlight, the dust, supermassive black hole emission, gaseous nebular emission are all interconnected with each other. So you really need a very rigorous feed-forward model that is able to start from generating stellar populations, modulating some of that starlight by Dyson sphere emission, and then forwarding that to how that would impact the dust emission within the galaxy or the nebular emission within the galaxy. And that's exactly what I've done here. So very similar to the plot that Eric showed with how a single star's spectra will change as you imply a Dyson sphere. It's just a fun model showing how see light from an entire galaxy changes as you change the percent of the stars going from 0% in the purple line to 100% of the stars being absorbed and re-emitted by Dyson sphere emission, where we see from a typical star-forming galaxy how we slowly start to transition to one that's nearly a pure black body emission with still some dust emission when we have covered all of the stars within a galaxy as Dyson spheres. And going forward in the future, I'm going to be using these models to perform similar searches to the Hephaestus project, but for all of the galaxies observed with WISE to see if we can see some outliers in WISE data that seem to follow this trend of Dyson sphere emission. And I don't have time to read all of these, but just some next steps towards observability. All of these people were pivotal in this workshop and writing this paper. Some of them are actually here in this conference, so if you see them, I know Daniel and Anna Maria are at this conference, so if you see them in the virtual hallways, stop them and ask them what they're thinking about with the Dyson Minds project going forward, and I'm sure they'll love to talk to you about the stuff they're working on. And yeah, with that, I'm going to leave my concluding remarks up that this is a really interdisciplinary and kind of fresh field of looking at what technosignatures we might be able to find around supermassive black holes or even any black hole in the galaxy. So if you have any ideas, but there's so much that still needs to be done, please contact me and we can put you in touch with the rest of our working group. Thank you.
All right, thank you so much, Olivia. Really great to hear about the workshop. And I'll have to check. Sorry, I'll have to check out that paper too. So we now move on to an extended discussion session. So we can have questions for Olivia. We can also have questions for Tongtian and further questions for Eric. So just please, again, use the Q&A box. You are also welcome to use the raise hand feature if you'd like. So right now we have a question for Olivia from Robin Corbett. Have you also considered Dyson Minds around stellar mass black holes or neutron stars?
Yeah, so we've talked not so much around neutron stars yet, but there's been a lot of discussion around stellar mass black holes, specifically and especially X-ray binaries as well, since the luminosities you can get from an X-ray binary are are fairly similar to the amount of energy that you can get from the accretion disk around a supermassive black hole. What Jason Wright is currently working on is going to be a sort of large project discussing all of the different ways that we've laid out for how you can extract energy from just a regular stellar mass black hole, ranging from just spin energy extraction, what type of efficiency gains can you get from that, and then some other things like one thing we're calling a stoking the fire scenario, where every year you throw a star onto the black hole and just extracts the radiative energy from that accretion disk. How long can you maintain that? Eventually, you're going to run out of stars, and the efficiency gain is going to start falling off. So yeah, so look forward for some time within like the next year or so a paper highlighting all of those ideas. But if you have anything specific, then we'd love to hear it as well.
No, thank you. All right. Okay. Caleb Strom, question for Olivia. Is there a reason that it would need to be a super intelligent extracting energy from a black hole? Could it just be the power plant of an advanced non-ASI civilization?
Yeah, so it definitely can be, and that's um also why we talked about in this paper that Martin Elvis is working on in this a biological habitable zone as well. Um, so yeah, so the main caveat that we had is that and another main reason why we were looking around supermass or black holes is that so far no planets have been detected around a black hole. So we're kind of working under the assumption that um, some that biological entities probably haven't formed around a black hole, although that might be up to debate. I'm sure there's been one claimed detection of an X-ray transit emanating from a quasar in the distant universe that may be from a planet. So maybe we do have planets around these objects that might be able to form life. So we were sort of working under the assumption that something had to have moved into this black hole. And you're right that it could have been power a power supply source a from some other entity, but we were just working under the assumption that this is going to be some super intelligence that sought the largest energy gradient to perform computations possible, and so started to migrate towards the supermassive black hole at the center of its galaxy.
All right. So I have, while we're waiting for more questions, I have a question that could really go to any of our speakers. I mean, maybe Olivia, since you did a workshop that explored this, but really, Eric and Tong Tian, you feel free to answer too. Eric mentioned this. He said, what do you do with all this energy? And that's a question I've kind of wondered. Like, one could imagine building a Dyson sphere or harnessing energy from a black hole or any kind of, exotic configuration to get this massive energy. And what would you do with it? And, I will just give a little background. I came at this kind of just thinking about Earth's future. And, there's some literature to suggest that there's a maximum per person energy consumption level that, like, beyond that you don't necessarily get much more returns in terms of a higher quality of life, and then you have increases in efficiencies. And so, perhaps, humanity, if we stabilize in terms of population, we may stabilize in terms of energy consumption, even while continuing to increase our standards of life for everybody. So I just think about if I project that into the future. It's like, when do we ever need a Dyson sphere? Maybe not. Now, that doesn't mean they don't exist and that we shouldn't look for them. But I'm just wondering if you all have thought about, what would you do with all that energy, and maybe what are sort of trajectories that would lead a civilization or society, toward that sort of extreme endpoint. So open to any of you.
Yeah, so I guess I'll start since this did come up at the workshop a little bit, and especially around supermassive black holes. I think the main reason that someone might need this much computation is to maybe a lot of the data processing for the experiments that they will be running. So a lot of the reasons that we're interested in supermassive black holes is just from fundamental physics perspectives. They're extremely interesting objects. And so maybe these sorts of large-scale fundamental physics experiments that they might be running around a black hole like this require insane amounts of data processing that we just can't wrap our head around. I mean, think of how much data processing is going to take to reduce and analyze all of the Vera Rubin observatory data, and I'll scale this up to computers and data collectors in a 1 parsec shell surrounding a black hole, and you might be able to scale yourself up to actually needing this much power output to perform these computations. So yeah, my answer is that for computations for sorts of experiments that they might be running just require this much energy, seeing as in our field of astronomy, our data requirements have been growing so exponentially as we start getting more and more data with every ongoing decade.
All right. Eric or Tong Tian, if you want to jump in, you feel free. Otherwise, no, we can move on then. Oh, go ahead. Yeah.
Okay, I think it's more likely there will be a flow from I mean, from the junior level Dyson sphere, which means the solar energy Dyson sphere, and move on to the stellar mass black hole Dyson sphere, and until the AGN and the supermassive black hole Dyson sphere. But I think, according to the observation capacity of the human telescope, equipment, I think the stellar level solar system, the solar energy that's sphere within the Milky Way is the most ordinary object. And as for the higher level, the black hole, which I used for the Dyson Minds, This sounds like I think much more extraordinary, and I think we would have less chance to find the evidence of them because it's hard to practice the follow up near the black holes, near the black holes. So this is my basic conception, my basic hypothesis.
Thank you. Very interesting.
Mm.
Okay, David Clements, would a tidal disruption event be damaging to these Dyson Minds or a benefit, giving a power boost? Similarly, for the usual variability of AGN, would they want it? In which case, one might search for enhanced variability AGN, or if you don't want it, in which case low variability AGN would be candidates.
Yeah, that's a great point. And we're throughout, yeah. So yeah, so would a tidal disruption event be beneficial or not? So there's obviously going to first have to be a lot of station keeping going on with the swarm elements as this object approaches, as a star approaches a black hole, enters the lost cone, and starts getting shredded through accretion processes. Since just looking at the S star populations around Sagittarius A stars, some of these stars can approach like within a tenth of a parsec of the black hole, which is going to be well within this 300 Kelvin computation shell that we've sort of been fiducially working with here. So yeah, so there's going to be um, a lot of station keeping needed. But as you said, it's going to produce an extreme burst of energy that they're going to be able to maintain, or that they're going to be able to extract. So maybe if they sudden, from an engineering perspective, if they suddenly need a burst of computing, they have just a lot of new jobs that they need to run. So they um, trigger or accidentally trigger a tidal disruption event in order to gain that energy flux. Um, yeah, so that's also one thing that we've been thinking about. But at the same time, maintaining this, uh, we can also imagine that a society like this that has become this advanced might be able to control like the orbits of these stars using something like Dyson's gravitational machines to change the orbits of these stars and throw them into the black hole in a way to trigger these tidal disruption events in a way that they might actually want. So we might be able to look like any periodicity in tidal disruption events might itself be a technosignature. If we ever are able to detect orbits of other populations of stars around supermassive black holes and find that they're all similar angular momentum, all within like the orbital plane of the supermassive black hole, that could be a fun technosignature of people lining up stars to just throw onto their furnace. Um, but then there's also the caveat that the core of a galaxy only has so many stars. I mean, it's millions and billions, but if we're talking extremely long-lived civilizations trying to create tidal disruption events every day, then eventually it might not be as if you might be using more energy to transport that star from an orbit from the bulge of the galaxy into the lost cone of the black hole. That just might not be worth it. So yeah, so there's a ton of fun things to think about with in those aspects.
Yep. Okay, so we have a comment from Clement Vidal. You may be interested, I think this could anyone as well, interested in the Stellivore hypothesis that he proposed in a 2011 paper. The idea is that black holes could be attractors for intelligence, links with X-ray binaries and supermassive black holes. So if you're familiar with that, if you have any thoughts.
Yeah, I'm not actually familiar with his paper, so I'd be curious to hear more about it.
Yeah, we could maybe discuss that on Slack. I've talked with Clement about that quite a bit, but yeah, maybe we'll take that to Slack because it would be a bit much. But I think, the idea could be if we think just, given that this day is themed about Dyson spheres and extragalactic and exotic technosignatures, if you think just about broadly the idea that black holes or neutron stars or X-ray binaries might have these high energy gradients that a entity might be interested in harnessing. Maybe this has very little or no connection to the place where human civilization's at, and there's a different kind of technological biological entity that can harness energy from stars and then move from star to star. So thinking about operating on very long time scales and big spatial scales. So we'll walk outside and harvest things from bushes. So you just imagine there's a different scale of life that operates where you can actually plan trajectories to move from one star to another, and we're going to go to that black hole system in this many millions of years because we know we're going to need the energy then. So just I think thinking about the problem on a very, very different time scale, and then thinking, well, could you look at these systems for something anomalous that would tell you like, oh, this is a living or technological system versus just a high energy one. Interstellar hunter-gatherers. Yeah, I think that's actually not a bad way to put it. But
Yeah,
if you, yeah, go ahead.
yeah, I think that would be interesting because it's very unlikely that an entity would like go straight from their home star system to the supermassive black hole at the center of the galaxy. So I do think there's going to be some tiered steps that they take along the way with like maybe their solar neighborhood, maybe they go after nearby X-ray binary, maybe they go after figure out how to deal with the environments around the neutron star or magnetar. So we might be able to like lay out this trajectory that some entity might take as they traverse across the Kardashev scale towards um, their original star system towards the extracting energy from the supermassive black hole at the center of their galaxy. So I'd definitely be interested in hearing more about those.
Yeah, we should share those papers in the Slack. There's also a comment from Robin Corbett asking if the Black Hole Workshop Dyson Minds paper is available.
It's currently, we just resubmitted our review a couple weeks ago. We were hoping to have it accepted by now, but it'll probably within the next month look for it on archive. And if the Slack channel is still up, I can send a link to it in the Slack channel as soon as we make it public.
Okay.
If anyone would really like a preprint, you can send me a message and I can send you I'll be happy to DM you one.
Good. Yeah, and then the Slack, yeah, you'll have permanent access to Slack. Everyone will stay on there. It's perfect. And then Joe Lazu makes a comment. I think this was in relation to my question that maybe there's a different maximum power efficiency for silicon-based entities, for sure. I mean, I think if we're thinking about technosignatures, not all of them have to have the same starting point as humans on Earth, for sure. There's many, or you do, and then you diverge. So many different paths. So David Clements again, if we're talking about uploaded or computational intelligence, they're liable to be under using quantum computing, which is likely reliant on low temperatures, low disruption from cosmic rays. Given the hot and radiation hostile environment of supermassive black holes, they might not be a good environment for superscale quantum computing. These conversations about this, sort of astronomical scale computing I find really fascinating. I see a lot of these, papers by, physicists and others on archive. And I mean, I come back, I guess, to the question I ask, what do you do with all this energy? But I mean, possibly, the answer you all gave me is on the right track. Like maybe we find that like you do get some benefits for investing such massive energy expenditures to, risk reduction or knowledge gain or something like that. I mean, we do this in some ways now. But so, what's the spatial scale at which that will continue or not is really interesting. So this has been a great discussion. We have no more questions. I'll just wait a second if anybody has anything else they want to say. To our speakers then, if there's no more questions, do any of you have any closing thoughts that you'd like to leave us with?
I guess with the yeah, I really hope the paper is an excellent resource for people looking to contribute to this field, and we really think it's a fun field with a bunch of low-hanging fruit for things to for things that anyone from astrophysicists to study practitioners to ecologists, etc., can get involved with. So please reach out to me if you have any questions or would like to um, be involved in our working group.
All right. Well, thank you. Tongdin, did you have anything you wanted to add?
I think that's all. If any, observation astronomers wanted to talk about the follow-up and scenarios about examination on the Dyson sphere candidates, feel free to talk to me, and you can also talk to Eric.
Excellent. Thank you. Eric, anything to say? You good?
No, I'm good. Thank you.
Okay. Well, thank you all. Really appreciated all your talks and the conversation. Thank you all for joining us. Let's thank our speakers once again.